Okay, good afternoon, students. Welcome to our first lecture from Heat Engines 3, or as we all know, Mechanics of Machines 3. Right? Um, yeah, it's good to be back. I lectured MOMS 2 last semester. I think it really went well. A lot of students enjoyed my approach in the subject. I think, and I'm hoping to make this one also enjoyable and challenging at the same time. What's nice is that we have uh, a book. We've got a prescribed textbook, and yeah, so it's sort of, I guess, arguably more structured. Yeah, which will aid you in which will actually aid you in. I'm hoping to maybe if I lecture the subjects next semester to just use the actual textbook. It's a bit tricky though, but yeah, so that everyone's able to. It's obviously a lot easier to follow versus having like individual notes and stuff like that. All right, so let's just go through the introduction, man. So guys, we'll be meeting on Wednesdays, 12 o'clock, but probably not 12 o'clock, probably at 12:30, 12:35, because I guess we have a lecture on electros, so a lot of students are burnt out, and then so we would just start a bit later. And of course, we've got periods till 3 o'clock, 3:30 essentially. We try to keep it within the time frame, latest 4 o'clock. But yeah, so maybe you just push till 4 o'clock, worst comes to worst, just to get through the content. But yeah, so Wednesdays, that's when I see you guys. Yeah. All right, so there are 7 sections to be covered for moms. I've aligned them with all the textbook chapters. And the way I'm kind of going through it, normally friction clutches is covering moms too, but honestly, it's not right. Because that will result in 8 sections of work being covered in one subject. In fact, excuse me, it's around 9. So at some point, I don't know really. I'll have to just really better sort out the section. Obviously, I've just inherited this from the standard, but yeah. So we're going through friction clutches. We look at balancing or rotating masses. Yeah, it's the reason why you see shafts maybe vibrate, or it's hard to basically correct that kind of thing, or even your tie itself, so you balance it. You look at things like that. In fact, there's also balancing or reciprocating masses, which we don't actually cover. So I'll talk more about it when we get there. We look at velocity analysis. Particularly, there's 2 methods, and this is where you're going to need your tools. Balancing and velocity analysis, where you essentially need your set squares and protractors. But there are 2 methods related to velocity and instantaneous centers. I might just cover the one because I'll tell you now the reason why. It's the same method for the same thing, but we'll see. We have forces in the reciprocating parts, discuss that, or inertial forces. Basically looking at a slider crank mechanism or piston reciprocating kind of motion, and looking at the forces, and you're basically building from the velocity and adding the forces and adding the inertial forces. It's particularly my favorite section. We also have energy systems, crank and effort diagrams. We're looking at the speed fluctuations, coefficient of fluctuation. Also finding how they actually find the mass of the flywheel required. It's a lot of graphs and stuff, and it's not particularly too difficult. Involute gearing. It's really just going to specifics of gearing. Looking at your path of this path of approach, your rubbing velocity, your length of contact, minimum amount of teeth, and use all this defining gearing terminology. And obviously, just lastly, gear trains. Now, gear trains wasn't done previously. It's normally done in the mechanical engineering department, so I've included that one. It's not too difficult, can be a bit tricky. So that's why I might just leave out one chapter on velocity analysis, unless we're not do gear trains, and then just do 2 methods on velocity analysis. So yeah, all the chapters are in. Theory of Machines. So that's the prescribed textbook for this. Like I was just saying earlier on when I was rambling, that hopefully I want to make it a part of the first moms as well. I just really need to look through it properly and try to make it kind of flow nicely. Yes, so that's quite nice. We have the structure. I'm also using the N6 Mechanical Techniques by Peter Toit. You'll see some of his questions in here as well from that textbook. You can buy that one. It's also fairly cheap to buy. It's, you know, N6 textbooks are nice, very straight to the point. They cut out a lot of fat, so to say. And also you've got the ON5 and ON6 textbooks. Of course, you guys probably seen those ones. You can also get those. There's also good examples. But obviously, I'll supplement Theory of Machines with as much resources as possible so that you pass. Right, so I said 7 sections here. Yeah, so for tests, 2 tests as per standard, 50-50, and your finals 100. The first test is going to cover 3 sections, or maybe in this case 4 sections, I think, or rather 3 sections. And then the last test will cover the last 3 sections, and then the final will cover all chapters. So just on the final, I always say for the final, the normal fees is that you might get a choice of questions. I might say you can choose the best out of, let's say there's 7 questions, right? And then you can choose the best out of 5 or 6, or maybe 8 questions, the best out of 6 out of 8, or something like that. But normally for the reassessment, I don't give choices. It's kind of, I tell you what I want. So obviously, I'm the one responsible for setting these exams, and obviously it's internally moderated and then externally moderated. But I'm still in the process of setting those. So obviously towards later on, you will obviously know what's kind of expected of you. But I'm not putting in the slide. So all tests will be on campus. So if you're on C, ideally finding a way on campus, probably have to make arrangements. But your final exams on campus is no negotiations. And of course, this is all depending on lockdown levels and stuff. So you really have to just bear with the department itself, or even myself, because things change all the time, and one will just adapt accordingly. It's important just to kind of you yourself work through the work, keep up to date. Because once test comes, you essentially ready. Of course, like I always tell my students, the slides or the scope, whatever we do here and whatever I say is essentially telling you what's going to come in. There shouldn't be any surprises within the subject. It's all within the textbook's domain. And if something extra, I will let you know. So for the first test, I'm expecting it to be in the week of the 13th of September. Obviously, as time progresses, I'll have the test dates ready for you. So I'll probably let you know towards, like, just before the holiday. The final holidays from the 3rd to the 13th. I need to just still filing the dates, all finalized but not finalized. Also the final, as discussed with the department, it's apparently it's basically the month of November. So we have basically August, September, and October to cover all our content and all our tests. So that's just the time frame we're looking at. I'm not obviously hoping that everything can go as planned. But yeah, just to let you guys know. But of course, all test dates will be communicated. You have at least 2 to 3 weeks to prepare for tests, so you should have more than enough time. Right, tools for this subject, guys. Old Faithful, Casio. You need to get that one. For this subject, let me think. Yeah, in fact, even the previous Casio would be fine. But if you can get this one, obviously get this one. I'm just looking at the chapters. Yeah, even the previous Casio, you would be fine. I don't think we're doing any complex stuff unless there might be a quadratic equation, obviously, maybe a 2x2 or 3x3 matrix. Highly doubted, but yeah, you probably don't really need this one in particular because you have the previous Casio. What you're going to need is set squares, Those are the big ones. I'm not sure the exact size. And maybe 30 centimeter ruler, obviously, maybe if you need that, and a protector, right, which is basically there. You're gonna need it for balancing in the velocity analysis. So you're gonna need those. For the other chapters, it's the standard what you're used to. Yeah, the maths on those it's not difficult. Obviously, it requires a lot of work, and historically the subject is taught using these tools. So I want to kind of keep it in mind. But yeah, I will obviously always just figure out better ways to sort out things. Some guys are probably tired of hearing this, and I'm definitely tired of saying it. But the first thing is always make sure you take notes and solve examples during lectures. That is key. Work with me through the examples. Do not sit and watch me do it. You're defeating the purpose of the way I teach. I mean, I talk, we work, and I talk, and then we basically kind of close the lecture. So we always kind of having small tutorial sessions within the actual lectures. Another thing, ask questions. I'm really happy with my students. They're always engaging with questions. In fact, providing further insight of things I do not know. I really like engagement, and I appreciate all my students always, making sure the lecture goes as planned, so we all learn. All the exercise in a notepad. In this case, not a notepad, it would rather be textbook. So make sure you complete all the exercises. In this case, it's a bit tricky to say 70 to 80% because some of the stuff doesn't have. Just start to complete all of them, right? Or 70 to 80% of them. You can gauge on what is important. Nothing too on the advanced level. But yeah, you would figure out. Most of you guys should know me by now. On how I kind of assess you. Check Blackboard daily student emails. Guys upload content always on Blackboard, so make sure you go check it. I can't be telling you go check this, go check that. Within a lecture, I'll tell you what to check, but always check. There might be some extra stuff, not to trip you up, but I always just add some stuff, extra questions, but it'll be in your best interest. If you see a question, work through it. All tutorials, yeah, I might send tutorials, not for marks. It's all and all past papers. So there is a past paper too. I'll probably post them, but wouldn't particularly need one for this subject. But I will post the ones that I have, which I've gotten. But it's like I said, it's all within the scope of the textbook, really. Rewatch all the lectures. That is up to you. You can watch as much time as you want. Watch the lecture. Ask me a question on WhatsApp. I'll try to answer it. It's becoming very difficult to answer questions because I have so much students. Oh yeah, I'll pull up the list now as well. Forgot about that. Also, watch additional YouTube videos. Guys, you can't beat YouTube. I mean, I can't beat YouTube. There is so much better teachers than myself who explains things. The Indian guys have solved every problem literally in textbooks. Make sure you go watch those. It's not about solving problems, but it's really about taking the understanding from those problems. Also, have 3 to 4 hours a day studying, yeah, that's all I can say. You need to work every day. That's no other way. You're not going to make this the semester without working every day. Monday to Friday, push. I always say Friday you can enjoy yourself, Saturday you can enjoy yourself, Sunday get back into it. Of course, when there's exams, you got to push. Just sacrifice this next 4 months of your life, get it out of the way. Obviously, some of you guys are going to go for autos, also go back to C and get your seconds. Obviously, it's a big benefit for you, the family. So just treat this time as a time of building yourself or meditation of some sort. Don't just say, oh, this is just more studying. Yes, it was so important that note of studying and passing. I was in the industry committee meeting with all the the AMSOL, the centers, and I can't even remember all those organizations over there. And essentially, I was presenting on the teaching and learning, but one of the guys said that they look for students of the first prize is students who passed all the subjects without fails. Funny enough. Secondly, maybe distinction. Obviously, that'll make you look good. That is first for real first prize, which is not always the case. Pass all the subject without fail. Secondly, is to have all your subjects. Thirdly, is to have all your subjects passed, and they look for those students. So, guys, the reason why most students fail is that they have these holes in their studying schedule. They block out 3-4 days of not doing anything. Then once you try to come back, it's a complete mess. So that's why I'm making you aware that Discipline is going to carry you. You know, winners don't need motivation. Winners need discipline. So guys, I can't stress it enough. I know it's and I really, it's a shitload of content to cover, and the stuff is not particularly easy. These are intermediate level concepts, not advanced concepts, intermediate. And you guys have enough intelligence to actually get through this. Just about hard work. Just about hard work. All right. Okay, so we can actually start the lecture. So who has watched the video before I actually start? The video on the clutches, by the way. Let's have a small discussion. No, you know, I'm just going to ask people here. So, Basong, do you watch the video I sent in the group? What you doing?
So I was actually just watching it now while you were going over the stuff.
Intro, yeah. So, Mr. Yeni, Mr. Mutawu. Oh, Ms. Nkuzo as well. She's here. So, I hope you guys watched the video on what it is. But in essence, I watched. Thank you. And you can just watch it again. And it's important to understand how clutch work, right? And what it's all coming about is this is about transmitting power, right? What I want you to understand is that, in fact, I'm going to engage a few questions with clutches. Who has any experience with clutches, whether it be automotive or on board? Can we just have a small discussion around that? I just want to get why do you have a clutch? Is it common on board? You guys overhaul it? You guys replace a clutch? Is it part of your routine maintenance? Can we get some of the experience owners to maybe just experience? Mr. Kuluse, anyone? If you know experience, just let me know so I can move on. I just want to see. Just so we can share. Is a clutch a common thing on board? If you can't get any, you must know. Thumbs up? Not really, that's what I thought, yes. Thanks, Mr. Kiefer. Nope, yeah. Sort of very common thing to do. Yeah. Flywheels, is that common? The flywheel coupled to the clutch. How do you guys change? How many speeds? Obviously, not a lot of speeds here. Anyone talk how the ship moves faster? How do we ensure that? Like, how does it all work? How do you provide more power to propulsion? How do you provide less power? Mr. Kiefer? Mr. Romanus, maybe? And Elisa?
So if you want to go faster, you just up the RPM. It's a direct drive from the engine to the propeller.
Yes.
No gearbox.
Here we go. Yeah, no need for transmission. Yep. Anyone else? That's the purpose of the transmission system, isn't it? Yeah. Anyone else? All right. You see, the reason why I do all these even small exercises is to like really just scope out the material. At some point when I'm on a degree program, if I am, I mean, we need to really look at the content and try to align it properly. Versus just doing new concepts. But nevertheless, friction clutches is a fairly interesting concept. Anyone else? Snazzle. You just increase it. Yeah, exactly. Direct drive. Yeah, it's all about making the engine work harder, increase the RPM. Yep. What else is there? I don't know what tunnel that is, but yeah. Okay. There is just a discussion there. Get some pictures on what a clutch is, and then actually the video has kind of replaced this kind of thing. It's a very elementary kind of thing, but you'll touch on it now. So, what is a clutch? Let's talk about it. So, a clutch is a device used to transmit torque between two coaxial shafts, two shafts next to each other, right? Top or bottom, horizontal, vertical, whatever. It enables the shaft to be engaged and disengaged while at rest and a little bit of motion. In fact, just we talk about transmission. Transmission is becoming such an old thing because, I mean, if you look at more modern or even modern like electric vehicles, we have motors coupled on wheels, and obviously to control that's easy, right? And obviously with motors, I want to touch on speed control and how we actually, like with pole changing and the frequency and all of that. And nowadays transmission systems are unnecessary. It's a very old school thing actually. And of course, the clutch was birthed through the transmission essentially. The need for transmission, because all the parts of the engine are rotating at different speeds, and you want to kind of manage that. You could even think of it as a speed management system. Nevertheless, let's say there's 3 things there that should be noted. So, some water. The contact surface should develop a frictional force that may pick up and hold the load, right? Or the reasonably low pressure between the contact surfaces. So just frictional force and low pressure is key there. Heat of friction should be obviously rapidly dissipated. Yep. Tends to be crab should be a minimum. And also the surfaces should be packed by material stiff enough to ensure uniform distribution of pressure, which is kind of interesting. That's what we're going to be talking about. I'm not going to touch on the particular coefficient or friction of the members of the actual material, or the elements, what I mean to say. But just important notes of the clutch, right? There's a bit in talk here between 2 different shafts. I like this one as well. We've got some gear changing happening there. A clutch is also a machine member. You have to connect the driving shaft to the driven shaft. That's also really important, right? So that the driven shaft may be started or stopped at wall, right? You start your engine, clutch is disengaged, you engage the clutch, you start changing the speeds, and of course that's what's happening on the car there, so that we have different speed ranges. A clutch thus provides interrupted connection between 2 rotating shafts. So two things are happening. We've got a crank moving, we've got the other thing moving, and we just making sure we're engaging the clutch in the drive shaft or whatever will move and engage, disengage, stay stationary, things like that. Also, clutches allow high inertial load to be started with small power. Interesting, like over inertia there. And popularly known as a clutch in automotive, or a popularly known application of clutch in automobile vehicles is used to connect the engine and the gearbox. Yes, that's what a clutch is. It's the speed regulating system, arguably, and of course it's like the child. The husband is the engine, the wife is the gearbox. I don't know if it's the other way around. And the clutch is the baby in between. Here, the clutch enables the crank to start the engine, disengaging the transmission, obviously, and then disengage the transmission and change the gear to alter torque on the wheels. So that's why you watch the video. You can see the thing talking about going up the gear, down the gear, up the hill, down the hill. Clutches are also extensively used in production. Yeah, that's also important. But this is like an old school way. I'm not particularly sure new production machinery with clutches, but clutches are a very obviously important device when you have a transmission system. Types of clutches. You got your positive clutches, right? Your dog or claw clutches. Then you got your friction clutches, which we'll be looking at. Particularly, we'll be looking at your plate clutch and your cone clutch, possibly your centrifugal clutch. I've never seen a magnetic current clutch or eddy current clutch. Very interesting. Or a dry one. I know exactly what it means. So even clutches are classified into, several things. Positive displacement clutches, right? So how they differ from your standard friction, which we'll touch on, is that your positive displacement clutches are used to transfer power where the velocity ratio must be constant, right? Interesting. That's when you want to use this. The most common type is the dog claw clutch. They basically use as to engage different ratios on the gearbox of a motor vehicle. I have this note here. It's the old note, and it says, I like this. And I'm reading it here. The gears in a motor vehicle are helical spur gears. Yes, I know that. Even I know that. And the exception of the reverse gear, which making gears always in mesh. Now, I like this one. So they say the different gear ratios are engaged and disengaged by means of a dog clutch, which slide on a spline shaft. Oh, let's give those too many things, eh? You know, too many things on AC pumps. On a car AC pumps. You will just show me a picture of that if you don't mind after the lecture. You educate me. It's exactly my end. Not a particularly clutch expert. I just know the theories, I guess, or the main theories. Yeah. So I said the different gear ratios are engaged and disengaged by means of a dog clutch, which slide on the spline shaft. And the grating sound, I don't know, I can barely do that sound. When a poor gear change is made, it's not caused by two gears failing to mesh. You know, obviously I used to think it's gears are like, I mean, gears are designed where they can nicely, obviously, this is what we do involute gearing in the chapter, like they can obviously mesh nicely. The reason why they mesh nicely, do with your denim and your amount of teeth and the diameter and all of that. And in fact, sound is happening, or the grating sound is happening when a poor gear change is made. It's not caused by two gears failing to mesh, but the two halves of the appropriate dog clutch failing to engage because they're both not turning at the same speed. Interesting, right? Interesting. And positive displacement. They're saying, yeah, the merits, they're simple, no slip. Obviously, you get a bit of slip on the friction one. Friction, obviously, friction to surfaces, obviously touching each other, they can slip. I'm sure you guys have had a clutch slipping before. And there's no heat generated. And it's compact and low cost. That should have been a separate point. Yeah, so these are just the main one. I don't want to touch too much on this. It's just positive. You do get these type of clutches. More for information sake than else. So, and obviously, it's the showing. Is it a car wheel or something? I don't know. So what are we looking at? Right, we're looking at friction clutches and disc or plate clutches, standard, single, multiple, which we'll be definitely looking at. Multiple just for more torque. And they are used when things are not running at the same speed. You see it? So previously, with your positives, you're looking at the same ratio. Yeah, it's we have NQ level 6. I can't ask that question. I might ask the difference between the two clutches anyway. So your friction will be used for initially running it, for not initially running at the same speed. And so in each of these type clutches, slipping will occur until the two shafts are brought to the same speed. So it slips, as it says, I should say, and once it's happened, torque will be transmitted with no slip unless the limiting friction force is exceeded. Now, obviously, the stuff will slip. A good way of thinking about that is back to our roll and slip conditions. Gave an idea of when the friction force exceeded or not. And the do kind of actually relies to think about the slip or the slip really. The slide, hold and slide or slip. All right. Yeah, so it's a nice local clutches I found on the internet, I'll post it up. I didn't reference it here, unfortunately. But what they say, what I like, they say it's two inertias, two rotating bodies essentially, traveling at their own respective velocities. And one of them may be zero, and they approach the same speed by engaging. Isn't that beautiful? A child, husband, wife, fighting all the time, have a child, clutch, brake, bam. You're all on the same speed. Beautiful. I don't know it's a good analogy. Any of you guys have better ones. And of course, slippage occurs because the two elements are running at different speeds. Obviously, there are two things rotating, and once a clutch engages, you know what I mean. The energy is dissipated through the actuation, resulting in temperature rise. Do we understand that? Are we happy with that? With how clutch works? Miss Jack, are you saying something? Did I explain it well? You have an idea? Yeah. So what's important is two things are coming together. And of course, there's slipping happening. Two forces are touching each other. I'm clapping my hands together, my fists. And of course, we need to have some kind of model to basically break this, to kind of see what we can do. Right. So what is this clutch? Right. This child or so. Some say. Just I don't know, remove a picture, guys. Just bear with me. So I was gonna take this picture away. Yeah, guys, I spend a lot of time preparing all this stuff. Yes, it's bloody crazy sometimes. So construction of clutch, 3 parts. engine flywheel, yes, of course. The pressure plate. And your clutch plate, the friction disc as it's there. So I'm sure you guys seen that. If you haven't done an engine overhaul yet on an automobile, I think you must go to hospitality. Or if you haven't changed oil. Or no, I'm just joking. I never did a service for a while before, and eventually I just realized I need to actually start learning. It's not that difficult, but it's good education. Yeah, I just move the text around. So say when the engine is running and the flywheel is rotating, right? Engine is running, start the ignition, it's running. The pressure plate also rotates, and the pressure plate is attached to the flywheel, right? That's also that's very important to understand. Flywheel is running with a pressure plate, right? The pressure plate has a diaphragm spring over there, some spring. And so you watch the video. What happens is, so Mr. Doyle, he decides the friction disc is located between the two, right? It's normally between the two. If you look at the figure 2 clutch construction, you've got the flywheel, the clutch disc, and you've got the pressure plate on the other side. Right? Obviously, the pressure plate's there for a reason. It's going to tell you. So, Mr. Doyle, obviously, this is now, I think automatic transmission obviously has a similar kind of setup, but you apply your pedal. When the driver pushes down the pedal, Mr. Doyle, the clutch is released, right? And the action forces the pressure plate to move away from the friction disc. So it moves away from the friction disc. And now there are air gaps between the flywheel and the friction disc. And between the friction disc and the pressure plate, no power can be transmitted. So what happens is essentially you push it down, it disengages, right? If I'm correct, yeah. If you leave it, it engages. I don't know. Yeah, it can confuse you. So they're saying when the driver releases the pedal, that's releasing it now, the power can flow. So it disengages. So when he engages it, doesn't flow. When he disengages it, doesn't flow. And now it's important, we touch on the springs in the clutch, force the pressure plate against the friction disc. The springs, that is why we saw those springs, which we'll be doing some calculations on. If you watch the video, This action clamps the friction disc tightly between the flywheel and the pressure plate. Now the pressure plate and friction disc rotate with the flywheel. Beautiful stuff. I never thought I would explain it like that, but yeah, you're just lucky. So yeah, I hope you guys get what a clutch is. And when we talk of clutches, guys, I want to ask one thing. What word in mechanics comes to you? Give me 3 keywords quickly. If you do formula analysis and looking at it, like what do you think of 3 words? Obviously, I gave you a few words now, but like, what do you think of? What variables do we need to model this clutch? What is important? Let's talk. I'm again trying to bring out your thoughts and what you think about stuff. For instance, force is a word, but what kind of force? Students, can I get a small engagement there, please? What is it all? Give me a few words there. The purpose of analysis is to fix your thinking.
Sorry, sir, can you repeat the question, please?
So, what I'm saying is what engineering mechanic words come to mind, you know, when you think of a clutch, like when we're trying to model, what are we modeling? Obviously, I have some words there, like what do we need, you know, like do we need pressure, you know, things like that. Temperature, I don't know, just anything.
Pressure, probably things like pressure, friction.
Yeah. I'm happy I got some words there.
Would angular acceleration or angular velocity be involved?
Yes, great. Torque, friction forces, man,
yeah.
Who is in Guanye? Yeah, rotational torque, inertia. Yes. Hey, I must add. Okay. Oh, anyway.
Oh, it's Shongwane. Sorry, Shongwane.
Oh, Shongwane. Oh, how's it? Okay, sorry. Fantastic. I know you're on.
All good, sir. Thanks.
Yeah. Yeah. So that's what I'm talking about, right? And always I wanted to think when you look at a body of not that you must be the expert, but like you need to update your software as an engineer to look at things like, okay, look at a coffee, right? There's a coffee, it's a liquid, there's density, temperature, right? You need to update your code to see things like an engineer, understand how those things works. So I'm just an easy play around, nothing really important. So the method of analysis, now let's say the torque that can be transmitted by a clutch is a function of its geometry and the magnitude of the actuating force applied, as well as the condition of contact prevailing between the two members. Two things touching each other, guys. Standard, you must think of friction, right? Something turning, torque, rotational speed. Then they're saying the applied force can keep the members together, and this is the key: uniform pressure all over its contact area. Of course, if the pressure doesn't apply on the thing, what tends to happen? It slips, right? There's not enough pressure to keep something together. You need enough pressure. And consequent analysis is based on uniform pressure conditions. So now we go to the two theories. So just to bear in mind as I go through this, there are two theories you're required to know for heat engines trees, particularly for friction clutches, which will be applied to all different kinds of clutches. It's your responsibility to know them and understand them. So the first one is the uniform pressure theory. Now I'll read it to you. They say this theory is based on the assumption that the pressure is distributed uniformly over there doesn't even look like a UDL, on the frictional surface, right? So we assume the pressure is constant. The normal force between the surfaces is the product of the pressure times the area. Obviously, force, pressure times area. This type of theory provides higher frictional torque compared to the uniform theory. Obviously, the reason why you touch that. And obviously, I swapped it around in the textbook, whatever. That's this note I gave. If the contact area is divided into a number of concentric rings of equal width, the outmost ring will have the largest area. The ring area is decreasing towards the center. The normal force per area will also decrease from the outer ring inwards. Nevertheless, right, what we assume here is that the pressure is uniform across the frictional surface. That's where the clutch is touching. But what happens? However, as time progresses, some wear can take place. Obviously, I think Pauline, Ms. Ramasuri, has a bad drifting habit. So she's always engaging clutches. She thinks she's living the Fast and Furious life. So a clutch starts to wear, right? What's not really mentioned here, wear is a function of pressure and velocity. Side note, just bear with me, you can read up on it. It's the old body of work on its own typology. And this may alter the contact pressure appropriately, and the uniform pressure condition may no longer prevail, right? So initially, these pictures are not right. You know, I'm looking at these two pictures and I'm realizing that this picture here is the what you call it, the wear, the uniform wear, and this one is the actual. So I've swapped the two pictures around, and this is the other one on the. No, in fact, the book messed up. So that's cool. I should actually tell the author. Nevertheless, right? So now this is more. So for you buy a new clutch. Well, you buy a new clutch at the spare shop. That's uniform pressure, and after the next 3 days, you're back on uniform wear, basically. And they're saying, what's the uniform wear theory? It's assuming the fit between the contact surface is perfect. Obviously, the normal intensity of pressure will be equal at all points. This theory is linked to worn clutches because wear is uniform over the contact area from the inner radius to the outer radius. And you'll touch on how the pressure distribution changes. Just forgive me with the pictures. The rate of wear between the contact surface depends on the intensity of pressure. Hence, I mentioned pressure is important, as well as the velocity of rubbing between the faces. Wear is relative to the product of the normal pressure and the rubbing velocity. So yes, we will discuss that. So two theories you apply. What is important, students? Now it's unpacked here. I should probably unpack it here. So we're considering a single plate clutch. Obviously, start on a basic clutch, and then you must know two things, right? If you look at the left-hand side, the uniform pressure, the formula is going to be P equals W, which is the axial force, actual force load on the clutch, and the force to keep it together. If you look at the schematic, a beautiful schematic, and we divide it by the area, which is pi r squared minus pi big circle minus small circle. Does it make sense? That's for the force. However, with the torque, it becomes a bit more complicated, and then we have this mean radius of friction surface. So it's 2/3 the bigger radius squared minus the small one. Sorry, it's cube and squared. Of course, this has come through integration. So they're showing you the integrate from the two radiuses. So understanding the uniform pressure, you've got a different force, and for your uniform, so you got a force there, and you got a radius. However, on Ms. Ramasori's side, she has uniform wear, and what happens there? The pressure, the intensity of pressure varies inversely with the distance. So depending where you are on the clutch, obviously it will change. So it's important to note at the inner radius, that's where you have maximum pressure, and at the end you have minimum pressure. All right. And then basically our force will be equal to P max times R times 2 pi R2 minus R1. So that's equation just above equation 7.28. That's another equation you need to know. And of course, when you're looking at the torque, your radius is not 2/3 anymore. It's just taking the average of the radius, because now it's basically kind of like nearly flat. No, I don't know if I'm saying it right, but yeah. So be aware that there's different force formulas for uniform pressure and uniform pressure and uniform wear. Likewise, it's different radiuses as well. And then this is kind of encapsulating all of this. Now I'm up to you. It's very small over here. What is torque equal to? Can someone just shout out for me? What is torque equal to? Come on, guys.
Force times radius.
Thank you, Avano. So if you look there on the frictional torque to what's transmitted to the clutch is basically R, which is the radius part, and we discussed the different radiuses for uniform pressure, uniform wear. That's in front of you there. And then we've got W, and W is an axial force, a minute force keeping the clutches together, which I'm clapping just to demonstrate two bodies coming together. And of course, we've got mu. Why? Friction, touching each other. It's the frictional force, right? And then we got N. What is N? What is N? Let's read it. It's note number 2. For a single disc or plate clutch, normally both sides of the discs are effective. So both sides are getting forces. Therefore, single disc clutch has 2 pairs in contact. N equals 2. Always remember that. You'll be chowed if you forget the 2. And then we talked about the different pressures, obviously, right? Minimum on the inside, maximum. I don't know what's going on. It's a bit weird. Just in summary, in the case of a new clutch, the intensity of pressure is approximately uniform. So, and in an old clutch, we use the wear theory. So sometimes in a question, I won't tell you what theory to use. I'll say you're busy with an overall and compute the torque before, torque after. Old means uniform wear, new means uniform pressure, right? And what's important to note of them is they say that the uniform pressure theory obviously gives a higher frictional torque than a uniform theory. Therefore, in the case of friction clutches, uniform wear should always be considered unless stated otherwise. Interesting enough. So if I don't say anything, uniform wear. Worst case scenario, obviously, right? Because the clutch is not always new. Beautiful, beautiful, beautiful. Next. Yeah, so if we play around with the formulas and stuff, and we can make new relationships with diameter instead of radius, that will be in a separate notepad. And I probably will be giving you these formulas, a couple of the ones that you need to know. This is like a formula, you know, for torsion that pi/16 dq times shear stress, or pi/16 times d4 minus big D4 minus small d4 divided by d minus big D minus small d times shear. It's like just more convenient relations to like, you know, quick ways to actually just solve the torque and stuff instead of going the formal route. Right, we're getting there. yeah, leave it on. So, how long have I been talking? Okay. Yeah, so single plate clutch, obviously this is where we started. Not going to explain too much, but just quickly to say the single disc or plate clutch is shown in figure 1.1. Consists of a clutch plate with both sides of face of the friction material, usually for rodo, and is mounted on a hub which is free to move actually along the splines of the driven shaft. The pressure plate, obviously with the pressure plate, is always inside, bolted to the flywheel, and the flywheel rotate to the engine crankshaft or the driving shaft speed. Yes, the pressure plate pushes the clutch plate towards the flywheel. Yes, that's the purpose of it. And we've mentioned this basically how it operates. So just again recapping on I want to the reason why that was there is to understand how clutch works, which I think is more important. So you guys can obviously just go through that. Again, it's explaining the operation of a clutch. I had another information, but what I'm just showing is like the bearing, the thrust bearing basically, and the diaphragm spring. And look, when engaging the clutch, it's going up, down, that kind of setup. Engage and disengage, just to kind of view the forces happening. I mean, I'm not obviously a researcher or have a PhD in clutches and stuff, but I'm not sure where the movement of clutches are. But obviously, I think it's all essentially just we're running away from transmission systems. Like same with we don't want inverters converting AC to DC, trying to push straight DC. But we'll see how it goes. Very important note is let's say consider single plate clutch. You consider 3 plates, flywheel, friction plate, clutch plate, and they say the pressure plate obviously, and there are 2 pairs of surfaces in contact, which is the one, i.e. the flywheel on the one side of the clutch, and also the other side is the pressure plate on the other side. So then the clutch plate is in between. And to find the number of surfaces in contact is the total number of plates minus 1. So you have a lot of plates, you're going to have to play around. So that N is a tricky one. You must be aware of it. All right, students. Now I'm going to work through this example. We've got some homework here, got the solution as well. And then, yeah. So let me work through these 2 examples, and then you guys can play around for a few minutes. Is there any questions? Was it explained well, or was I lacking somewhere? Can we have a 2-minute discussion on that? Please, students, are you guys tired now? Students, are you there? Guess no one is listening. Damn. Any questions?
I'm listening, sir.
Yeah.
No questions, but confusion anyway.
Yeah. What's up?
No, I can't put a finger on exactly where. I'm gonna have to go back and I'll work through the examples obviously, but I will have to put up some extra work into this.
Yeah. Is it about the theories and so on? Like what's bothering you? We haven't started anything. I mean, I'll just talk. Yeah.
Yeah. No, nothing specific at the moment. I just my mind isn't all here at the moment. I'll be honest.
Okay. No, it's fine. It's fine. Thank you for saying that. Anyone else? Thank you, Mr. Zamp. Appreciate it. Anyone else? And Lisa, Bradley. I'd like to hear your opinions. Mr. Kuzo. Thank you guys. Yeah, anyway. It's cool. I just hope it was clear. Right. Let's quickly see. So just 2 examples, eh? Let's so far it's okay. Thank you. Okay. So I'm gonna push through these examples, and then I'm gonna give you 2 practice problems to work through. Right? And yeah. And it's gonna be like a small class exercise, obviously. I'm hoping to finish clutches by next week and start balancing as well. So it's not too much stuff. But if I have since a few clutches, it could throw a spanner in the works. Okay, let me just quickly start Yeah. So first example, in your theory of machines textbook, determine the maximum and minimum average pressure in the plate. Clutch force and the actual force is 4 kilonewtons. So right, the inside radius is 50, the outside radius is 100. Assume uniform way. Okay, this is a very small example, just detailing the pressure thing, just to make you aware of it. So just give me a second. Checking on the textbook exactly. Chapter 10, guys. Page is this? Page 302. Just so that you know. Okay. So where are we? Where are we? Where are we? Okay, I thought I wasn't even recording. So let's just quickly see here. So first thing is first. P max. Oh, okay. So this is the we just be doing this example, by the way. It's page 302. P max. It's on the inner side. So we're gonna say R2. What we're looking for. Okay, where should I start? So your force for your uniform way, right, is 2 pi C R1 minus R2, right? That's for UW. They call it UW, right? Just gonna go back to my slides and show you. That's why we have textbook. That's why I'm deliberately not giving you. I need to kind of go through it as well.
Sorry, so are we doing the top? Are we doing the top one or the bottom one first?
Yeah, the top one. That's what I said. Yeah.
Yeah, I thought so.
Top one. Yeah, cool. So the actual force is 2 pi R2 minus R1, right? So what we need is the C coefficient over here, right? And it's just some coefficient of pressure. So you take the actual force, 4 kilonewtons. You never get asked this, but it's just to make you aware. 2 pi R2 minus R1, not squared, be careful. That's this formula over here. Making you aware what we're using, this model. And what are the radiuses here? So it's 0.1 minus, that's basically outside minus inside, obviously. Just bear with the and 0.05. That's going to give you C. Where we're heading toward this is that P max is equal to C times R or R1. Okay, we know R1 is small, right? So don't worry about it. And R2 as the big radius. The outer and the inner, right? And in P min is going to be C R2. That is that uniform, that ununiform pressure we're talking about. Am I even doing this right? Like that. So you're basically getting that pressure there, that pressure. So what is my C equal to? And the unit's going to be Newton per meter squared. So what is it equal to? Can someone work it out for me? So you want the maximum, minimum average pressure in the plate. Guys, very basic example. Yes, Mr. Kawa. Oh, flip. Wait. No, that's probably a mistake. Wait, Mr. Mzam. Let me just quickly see here. We've got 4. We're dividing by that. We left with C. Yeah, I mean, why is this confusing me? Am I missing out on something here? P equals R2 and C, which we need C, right? So yeah, let me just quickly see. Yeah, I'm just confusing myself here. So what is C equal to? 112.732. Give me too much big numbers. Yeah, there we go. That's decent. Yeah. And then all we have to do now is basically just I could be tripping.
Sorry,
find
so
the
that's
maximum.
that's kilonewtons per square meter.
Yeah, thank you. Yeah. So times 10 times now R1, and I'm just feeling like I'm slipping here. I don't know why. I'm sorry. The maximum pressure is R1, which is a smaller radius, and which is going to be 0.05. And of course, this is supposed to give us. Yeah, let's just see what we get. Let's see what we get. Let's see what we get. Let's check if my calculator is it. Because the units are not like. I'm not sure if I'm okay with my units here. No, my units are not right here. Can't be. That's not the right unit here. That's Newton meter over. This is going to be Newton meter. C must be Newton meter. It has to be anyway. It's fine. It's just a coefficient. Let me just see. Just to find, just to check maximum minimum pressure. Just be aware of the formula you must use. My max pressure is 636.5, which is definitely wrong, and I'm trying to figure out where am I tripping up here. Why? What am I missing here? Oh, this is what I'm missing, guys. You remember, this is only yeah, but I just found C. That's all I really need. Oh, but you see here, this. I'm looking at this particular model here. Okay. But your maximum force must have this P maximum. That's what's missing. So yeah, that's why this is in Newton meters, and then if you have the Newton, so yeah, my mistake was here. Here we go. So that's then we have P max here, right? P max and then C. So we have to really just I have to really just adjust things. I made a mistake. Forgot again. It was pressure times area, obviously. That's the idea. So let me just redo this. Okay, so we have W equals P max. C. Okay, P max times C bracket R1 or R2 minus R1. No, you're just gonna have it like that. Okay. P max, right, equals, remember this is for the maximum condition, it's C times 0.05. So I'm sure we can substitute we want the pressure as P max divided by 0.05. That equals C. So I think we can substitute this here. I think I'm doing the right thing here, guys. I'm going to worry here. 4 kilonewtons times P max going in here. That's going to be P max squared times 0.05, and then so this is equal 0.1 minus 0.05. Look, I think I'm doing the right thing there. Sorry about that. Just really for understanding, guys. So yeah, just my answers are looking vaguely very funny, and I'm not sure what's going on, what I'm doing wrong. Why? What is going on here?
Yeah, so sorry. Why is it?
Oh, yeah, I see your mistake. I see your mistake, man. I know what I'm doing wrong. Yeah. C is equal to pressure max times radius. That's the mistake I'm making. Yeah. There we go. But then that's the same thing, is it not? Because I'm substituting P max times radius here, and I'm gonna get P max squared. Yeah. Not sure exactly. What answers are you guys getting? I'm looking at the book in front of me. They have 0.2546 Newton. Oh, they have zero. The answers are probably right, man. It's probably the units. Let me just have a look again. Go for it. Yeah, I don't know. It's probably my units. So if I get that answer, let me just quickly check again. Yeah, I get on this side 16, 160 P max squared. Yeah, this should be right. Yeah, P max or yeah, fine. Then if I root in, my pressure just doesn't look the same here. So I really don't know what the fuck is going on, honestly. 64.9 kPa, right? And then your minimum pressure, you basically do the same thing now. And then C, in this case, your P min, so P min, I know what's going on. I'm using the maximum pressure. Yeah, no, whoa, that's right, it's 0.05, yeah, so it is 50 mole, right, 50 mole. This is just going to be P min. Don't worry about it, man, I don't know, it's fine. And this should be 0.1, and then you're going to have 4 kilonewtons divided by 0.1 times 0.1 minus. Yeah, someone's going to probably pick up where I messed up, but I'm just checking two pressures, and this is P min now. And then P min will be 4 kilonewtons, 0.1. Of course, this must be root, I think, rooted. Yeah. So P min is 894.427. Yeah, still, I guess we're right. I mean, I don't know what I'm doing wrong, but it looks Newton per millimeter squared. And I mean, that's just going to be times 10 to negative 6. So I'm not really sure what I did here. 7, maybe somebody can just pick it up for me at some point. Nevertheless, yeah.
Well, I think your first approach was correct because it's this one I don't understand it.
No, it's right. I'm just looking at the book's answers. It's fine. You should not worry too much. Just, I mean, inner radius is a maximum pressure, and the lower radius is a minimum pressure. And this coefficient, which is this coefficient over here, which is the intensity of pressure, which is P times R equals C. So now we just, if you look at this here, so this is P times, what I don't have is a 2 pi thing. Yeah. This problem wasn't meant to be this confusing, you know. It's just like, what the hell? P max, and R1, yeah, 2 pi. Because this is C. This here is C. I see. You know, guys, honestly, yeah, I see the problem. But then that's not going to give me the right answer. Let me just quickly check here. Anyway, okay. So bottom line is you have a maximum pressure and a minimum pressure. And for you to find the average pressure, all you basically have to do is basically, let me just have a look here. It's not on here. If you're looking at basically So for uniform wear, the idea is that basically for uniform pressure, you have a uniform pressure. Whereas for uniform wear, you have something like this. And what I was just trying to illustrate was like the two pressure limits. So I should have just went to the books approach instead of having all this confusion. But it's not anything much than just knowing that there are two pressures happening and basically all. So don't worry too much about it. So just forgive me for that little mess there. So it's a very small example. It probably won't be, you'll never be assessed on it. So just an example in the text. Paste. Okay, so now we get to the real nuts and bolts here. This is how a typical question might be. Okay, so here we got a single plate clutch with both sides effective as an inner and outer diameter friction surface, 250 and 300. Diameters, the maximum tension pressure is, that is the C, 0.15 MPa, and the coefficient is 0.3 turn for the power transmitter of the clutch. At the speed of 2,400 for uniform wear and uniform pressure. And this is what I actually want to touch on. But just be aware of the difference in the pressures, where the minimum, where the maximum is. That's what I really care about really. So it's important to understand our torque formula, right? Our torque is going to be N. N, W. What else am I missing here? There are two things. Guys don't know anymore. Mu and R, right? Okay, so here we're going. U, W. So this is like, you could follow a standard approach of how you would actually do this. You'll see. So the first step we normally do, we need the force, the radius, and for uniform wear, if you remember, oh, let me just copy that. That's what I was trying to do. So I just want to see. Hey, Jesus, right? Why can't you expand? Okay. Just wanna the logic for some reason. Let me just copy what I want to copy here. So the first thing you must do now, there we go. Move it over here. The first thing to do is for uniform wear is calculate. You can start with your mean radius. So your radius will be R1 plus R2 divided by 2. In this case, that's 0.175 plus 0.125. That's all we're looking for. Divide that by 2. Well, what answer do I get there? Can you guys give me that answer? Okay, so that's 0.175 plus 0.125 divided by 2. That's 0.15 meters. Okay, yep. Next is, so to find our basically C, 2 pi R2 minus R1. And remember, C is equal to P max times R1. That's basically what I'm talking about here. So your maximum intensity of pressure is given to you as 0.15 MPa. It's over there. Very simple, guys. One must just know what one must apply here. Right? You times that by your remember your smaller radius, that's C, so that's R1. This is what C is. So R1 was 0. That's what the maximum occurs, so 0.125. And of course, your 2 pi R2 minus R1. So 0.175 minus 0.125. All right. Can I have that can I have that answer? Not squared, guys. What is the answer? In newtons. Answer in newtons, please. Let me see if I agree. Yep, 5890.48. Is it 5890.5? Is it? 5890.48, sorry. Beautiful. My next question is, we've got this guy, we've got that guy. Our coefficient of friction obviously is always given to us, 0.3. What is my end value for single plate clutch? Someone please tell me. Let's see the experts. And why? Why is it 2, Mr. Kiefer? On the reasoning.
A clutch just has two sides to it, and both sides are effective.
Yep, beautiful, beautiful. Dr. Kiefer as usual. So torque is equal to 2 times 5890.48 times 0.3 times 0.15. And what is my torque there? After this problem, we will have a short break and then we will continue. Could I have my torque, please? In fact, from my torque, goes straight into your power as well. So our speed given was 2,400. 2 pi nt, guys. You cannot not know this. Let me see the torque. Let me see that torque. 530.14. 530.14. Beautiful. So you can see like how it's typical that you must know this is system maximum pressure, doesn't it? It's kind of a must. Anyway, so my power. How much power do I have there? Around 133 maybe, I think. Just work it out yourself. Yeah, 133.24. Yeah. Beautiful. Uniform where? Oh, well, my MPA. Now, the question's gonna go. Dr. Kiefer, decides to replace his clutch, right? He decides to replace his clutch. What will the power output be now? So we're going UP, right? And I'm gonna just enlarge everything. So UP, guys, you've got a new, I'm gonna just leave it like this. You've got a new force formula. The force now is pressure, the intensity of pressure times pi r squared minus r squared, big minus small. And the new mean radius is a lot different. And we're gonna probably see why. Yeah. So I like you guys to calculate now for the same parameters. I'll just, of course, you should remember. That's why 350, 250, C was 0.15. Let me just make sure I'm right. But C, obviously, for this, you don't need C because we have uniform pressure. So this doesn't become a big factor. So all you basically need is those over there. I hope you guys understand that. Quickly do that. I'll give you like 5 minutes and I'll quickly run through it. Some just put the torque in the power once you're done. I'm still recording you. So let's see after the overall what happens. Oh, you win. So anyone get the power and torque? Anyone?
Sir, can I have the RPM? The
2,400.
Thank you.
All right, so the first thing that you want to do is calculate your mean radius on the friction surface, which is Rm, right? And as I said, it's 2 over R, R2 cubed minus R1 cubed divided by R2 squared minus R1 squared. And can someone give me that value? I'm sure you worked that out. What's R2? Times. Okay. You get a mark, obviously, for using the right theory. And also obviously find this mean radius. Who got one? Was it what? 151.4. 0.15139 meters. Of course, your we do need oh no, we just need we do need the intensity. I was lying to you. I made a mistake here. P times pi R squared 2 minus R squared 1. So that's going to be 0.15. Let's make sure. Ivana, what is your power? 175 squared minus 0.125 squared. So you should get 706.8.583 newtons. Surface in contact is again 2, and our torque formula is exactly the same, so it's 2 times 0.3 times 706.8.583 times, what's it again? 0.15138. What's my torque? Students? Should get around 642.1 Newton meter. Can everyone agree with this answer?
Sir, I got this 642.06, but I did it differently. Like my way was very different.
Yeah, but I mean, this is the only thing you should really done. You should get this. It's not that complicated. So, how much is your power? Sorry?
Yeah, I got no. That's my torque. My power,
Yeah.
I got 161.368.
That's right. That's correct. Yeah.
Yeah, but I use the force. I use the same from the previous one, 5890.
Yeah. Now your force shouldn't be the same. Your force is different. It can't be the same.
Yeah.
Just letting you know. Yeah, it shouldn't be the same. Yeah, obviously. So if you do this, but your values, it sounds right. I don't know what you did here. So there should be different forces, obviously. That's how you get different torques. So let me just make sure my stuff is right here. Man, what am I doing here? 2 pi nt, 2 pi. I don't have 2 pi counterpart here. 161.377 kilowatts. Students, are we all happy with this? People are awfully quiet here. Let me just see. Mr. Bason, are you good? Mr. Matt? And Elisa, are you good? Monsanka, are you good? You guys get this power? Yes. Okay, fantastic. So what I want to say, can you just see the disparity in power? So you have a new clutch, you drive for a while, and look how much power you lose, right? Can you compute in percentage how much power was lost? In fact, not how much power was lost, how much power was gained. Thank you. How much percent power was gained in percent form? Let me see. 161.377. Okay, so we're gonna say, is it 17% gained? I wonder. Yeah. So guys, replace your clutches. Now you know why. This is what's happening behind the scenes. All right. So before we hit on to our small tea break,
Sir, just before
yes.
the tea, up
100%.
there, where's force is equal to P?
Pi r squared minus big R squared minus small r squared.
Yeah, it's P pi. This P is pressure.
Yeah, the pressure coefficient thing. Yeah, that's 0.15. Yeah.
Oh, the C.
Yeah. It's not,
All right.
no, the C is P times R. It's just follow this approach, you'll be fine. We'll discuss.
All right.
Yeah, P is,
All right.
yeah. Yes, Silas.
Yeah, I also have a similar question to Motos. You see that one, because I'm also getting confused. That P, because okay, I'm checking on the book here. They said P makes R is equal to C, so to say. But then,
Yeah.
what does that PR replace in the formula when you say W equals to 2 pi C R1 minus R2? There, I'm getting confused there. Can you maybe just explain to me there?
Yeah, okay, so that's fine. What we're going to do is do two examples. You're going to see. But normally that pressure coefficient will be given to you. That's 0.15. And you have to find C. So what I'm showing you is just that approach. Once you do more examples, it'll clear itself. It'll clear by itself. But normally for uniform wear, you must be aware that, just remember, let me write it here. I just realized my Coke is a bit thin. I want to show you guys something else. C equals P times R. This could be max or could be min. That's what C equals to. But of course, in uniform wear, we go over the maximum power. In this case, that pressure there it's normally given. But we need to go through a few problems and you will see it yourself. It will materialize by itself. That's what I'm trying to say, but you'll see. So just please bear with me. And then the last thing on this note, before we get into the other stuff, is, where is it? There are the convenient formulas which I talked about, which are nicely derived in terms of diameter, and they all look like this. So you see there? So for uniform pressure, we can use those formulas on top. For uniform wear, we can use those, but always remember C equals P times R1, which is the maximum pressure. So this is more convenient ways. One's with diameter, one's with the radius. It's exactly what we're working through here.
Yes, sir.
No.
I use this formula on uniform pressure, the first one. I got this
That's
600. Yeah.
Yeah. No,
Without
I'll
using-
see by your own. Yeah, no, it's fine. You can use this.
All right.
Obviously, the way I'm trying to teach is like, I can't just show you this, just end up fucking over. Anyway, sorry. But yeah, like, just so you can see. Obviously, this just in terms of radius. One is in terms of radius on the left-hand side, and one is in terms of diameter. So you can, doesn't really matter according to me. All right, let's go on a 15-minute tea. So that we can refresh our minds. I know it's a lot of content for some of us. But is there any? I'll take a quick round of 2 minutes questions, or 2-3 minutes, and then we will continue with clutches. But it's very basic, guys. It's nothing crazy. Any questions before we go on tea?
So I have a question, sir.
Beautiful.
What notebook or textbook are we using? Are we using that theory of machines? Is that the textbook or the notebook?
That is correct. Yeah.
Okay, all right, sir.
Yeah, Brent shared that. So yeah. Obviously, I'm just choosing. I found some other examples just to highlight the approach, man. Obviously, maybe a better way of doing it. I think maybe worse, but yeah. But if you on that textbook, you should be good, man. But I will be saying I'll be putting a lot of extra questions, obviously, as per normal. Yeah. What's important is to know the two different theories. I think what I'm highlighting here is know there's two different theories to model clutches, and look at the importance of actually replacing the clutch, or, you know, and that kind of thing. So it's yeah. Okay then. Let's just have a small break. Probably what time is it? 20 past 13 minutes. Yeah, let's come back at 22. It's 22. How many minutes is it? Yeah, 25 minutes. Okay. And then we will just conclude, not clutches, but obviously this part of clutches. Yeah. Okay then. I'll just stop